Okay, so right now we are going to go over Unit 11, Worksheet 5, Analyzing Circuits, Circuit A. So what we have for Circuit A, we have a power source, we have one resistive element here, and then we have two more resistive elements over here. And then this is going to be a closed loop. Everything we need for a circuit. So this is a complete and functional circuit. When we are analyzing our circuits, the very first step we do is we write down what values we know. I know that the resistance for the battery will always be 0 ohms. I am told that the resistance of resistor 1 is 10 ohms, resistor 2 is 4 ohms, and resistor 3 is 4 ohms. What I also know from this circuit is that the voltage is going to be 24 volts for the voltage of the battery. And then the last thing I know is that our current is traveling in a clockwise direction. So it would end up leaving the power source, traveling through resistor 1, continuing to the right before eventually entering this node, splitting up into two paths before eventually coming back together again down here. And then eventually making its way all the way back to the power source. So that's what I know at the beginning. Once I know that, then I can move on to determining the equivalent resistance. Previously, we've gotten practice with determining the equivalent resistance for resistors in series or resistors in parallel. What we have right here is going to be a mixture of both. So when you see that, I'd recommend redrawing the circuit in a way that kind of makes sense. It doesn't need to be like a huge redraw, just something quick and simple to draw an equivalent circuit. When we draw an equivalent circuit, the power source is going to stay the same, so we still have 24 volts for our power source. I am going to leave any resistor that is by itself, just by itself. For example, R1 with that resistance value of 10 ohms stays where it is. But because I have resistors 2 and 3 that are in parallel with each other, I am going to draw my equivalent resistor for resistors 2 to 3. But I don't know the value. So when I do that, I need to determine the equivalent resistance of resistors 2 to 3. So REQ 2 to 3, we're going to take our 1 over resistor 2, so that's 1 over 4 ohms, plus 1 over resistor 3, also 4 ohms. And then once we add those together, we take the reciprocal. So I will end up with 2/4 to the negative 1, or 1 over 2 to the negative 1. When I flip that, my equivalent resistance is 2, and the units are ohms. So this right here is going to be equal to 2 ohms. Once we have that, the equivalent resistance of this entire circuit for resistors 1 through 3 is going to be, well, resistors in series. So R1 plus R, well, equivalent, 2 to 3, which equals 10 plus 2, or 12 ohms, for our equivalent resistance of this circuit. The reason why we needed to do that was so that way we can use the equivalent resistance when we're trying to determine the current that is flowing from the battery. To do that, the current from the battery is equivalent to the voltage of the battery over the equivalent resistance of the circuit. Note, this is going to be a rearranged version of Ohm's law. V equals I times R. We just rearranged it for the variable we're solving for. The voltage of this battery is 24 volts, and the equivalent resistance of this circuit is 12 ohms. So there are 2 amperes of current flowing out of the battery. So 2 amps flowing this way, and as long as the path is, well, unbroken, it will always be 2 amps. However, once we enter that junction, where we have those 2 resistors in parallel, that's where our resistors will not have the current of 2 amps, but their individual currents will add up to that initial entering current of 2 amperes. But I can write down the ones that I know. The current flowing from the battery is 2 amperes. The resistance of resistor 1 is 10 ohms, and we have a current of 2 amps flowing over that. If I know both the current and the resistance, I can even calculate the voltage. So the voltage drop across resistor 1 is equal to the current of resistor 1 times the resistance of resistor 1, just using Ohm's law. So the current is 2 amperes. The resistance across resistor 1 is 10 ohms. So 2 times 10 is 20, and the units of voltage are 20 volts. So we have 20 volts for our drop in our voltage across resistor 1. What that means is if my V1 is equal to 20 volts, and my V battery is equal to 24 volts, using Kirchhoff's voltage law, the voltage of the battery is equal to the sum of all of the voltage drops in the circuit. We can end up using this and solving what the voltage drop across resistors 2 and 3 are. Because I know that my voltage 2 to 3 is equal to the voltage of the battery, 24 volts, minus the voltage drop across resistors 2 and 3. Oh, and then that's going to be minus the voltage drop across resistor 1, so minus 20. So the voltage drop across resistors 2 and 3 is 4 volts. That's going to be 4 volts for both of them. Because what we have here is when we have that voltage drop, it doesn't matter which path the current flows through. It would have that same drop of 4 volts going to the left path or to the right path. We still have that 4 volt potential difference drop. So the voltage drop would be constant regardless of which path the current flows through. So now that we have this, we can end up determining our equivalent current for each of these. We're going to have, well, for this one it'll be the same, but sometimes it'll be different. So when we do that, the current flowing through resistor 2 is equal to the voltage of resistor 2 over the resistance of resistor 2, or 4 volts over 4 ohms, which will be 1. The units of current are 1. So we're going to have 1 amp of current flowing through both resistor 2 and resistor 3. Now the last thing that we need to do is to determine the power. Power is equal to current times voltage. Now if we're solving for the power that is generated by the battery, the power of the battery is equal to the current of the battery times the voltage of the battery. 2 times 24 is 48. For the power dissipated across resistor 1, 2 times 20 is 40. For the power dissipated across resistor 2, 1 times 4 is 4. And for the power dissipated across resistor 3, 1 times 4 is 4. Now, this is where we can actually check our answers. Because if we have 48 watts of power that our power source is capable of providing, then all 48 watts of that power should be dissipated across all of our resistors. So we just add up the power dissipated across every single resistor in our circuit and make sure it matches the power that was generated by the power source. So 40 plus 4 plus 4 equals 48. So that is a good indication that we ended up solving for the correct power in each of these cells, as well as for the rest of our properties across the entire table. So to summarize what we did once again, first thing that we do, just look at the circuit diagram, write down what you know. Then, after that, determine the equivalent resistance. When necessary, redraw the circuit for its equivalencies, which I did just by taking those parallel resistors and drawing them as an equivalent resistor that was then in series. Once you've either redrawn and determined the equivalent resistance or just determined the equivalent resistance, then you can use that equivalent resistance, the voltage of the battery, to ultimately determine the current that is provided by the battery. Once you're looking at that flow of charge or the current from the battery, you can apply Kirchhoff's current law to see which resistors have the same current as that provided by the battery, which ones would have a lower current that got broken up because of the multiple paths. Then you can use Ohm's law and Kirchhoff's voltage law to end up solving for any voltage drops as well as any remaining currents that were unknown. Once you've filled in the current and voltage columns, then you can just apply the power equation. Power equals current times voltage to determine the power that is dissipated across each resistor.